Okay, so thank you. I don't see any raised hands to the people who would like to ask questions to Dario. So we can start the general discussion, and you can ask questions to any of our three evening speakers. So please ask questions to Augusta, to Per, to Dario as well. Okay, Alexei. Alexei Sharapov.
Yes,
please.
I have a question to Per concerning this gauge Poisson sigma model. May I think about your gauge Poisson sigma model as just conventional Poisson sigma model in some extended superspace? So you start with usual Poisson, break and then extend it somehow and write down the conventional two-dimensional Poisson sigma model, or maybe this is another class of topological sigma model. Could you clarify?
You think exactly correctly. It's you can introduce a B super vector field. Okay, instead of a B vector field, you have a B super vector field in target space. You can write down the model in that language. However, that breaks the manifest diffeomorphism invariance down on M, on the base M. You work on this tangent bundle, shifted, Harriot shifted tangent bundle, T1 of M. And there everything looks like a super...
Okay, so in some sense, this is a specification of Poisson sigma model on some supermanifold.
Yeah, you can have like n bosonic coordinates, n fermionic coordinates, and super B vector fields. Indeed, but then there are a couple of details here. First of all, it becomes manifestly diffeomorphic invariant down on M, okay? And that's not, you know, that's a detail, but that was demonstrated in the paper with Cesar Arias and Alexander Gomez, how you get manifest diffeomorphism, and that requires a field definition involving the connection.
I'm asking because sometimes people consider what they call twisted Poisson sigma model by in some two forms of that.
And there is another thing with this additional term. I had this d phi plus theta. So the additional supersymmetry here appears, of course, when m equal to n. Okay, so you have equal number of fermions in bosons. And then finally, what was important for the whole construction is this additional shift symmetry that we reported on in a separate work. That supersymmetry is they're of different type. The first one is just the BRST, you know, sits in the BRST differential naturally by adding that term. The second symmetry is one have to struggle a bit more. I didn't give a lot of equations here, but you have to put conditions on the background. The curvature tensor has to be constrained, etc., etc. Then you have this additional shift symmetry, and those geometrical constraints are equivalent to having a fibration. But it is just, as you say, I mean, in principle, you can have a much, you know, you can think broadly of supersymmetric target space supersymmetric theories or target space bosonic fermionic theories, B vector fields, and start reducing it. And then, of course, you have additional structure for the gauge.
Thank you. Thank you.
Okay, any other questions, please? Augusta, you can continue your answer to Misha Vasilyev.
Yeah, I can do that, but I wanted to ask something to Per, actually, just to see, because I couldn't follow the details of what you were doing, but I just have a feeling. I mean, you start with sigma models, but in how many dimensions are they?
Well, they're in, we had first quantized models. They're in 1 and 2 dimensions.
Ah, okay. Then you go through a first quantization, then a second and a third quantization. Okay.
Then you scratch.
I was wondering whether this kind of route could give you, I mean, since we have a long-held feeling that somehow the Vasilyev system should be related to some singular limit of the open string where you look at the first Regge trajectory, you know, with all the difficulties that you have to be not in flat space, but never mind. Now, is it possible to conceive that a sigma model construction of this type, since it builds the Vasilyev equation, could give you a worldsheet description that can be associated to them?
Well, I mean, that was part of our proposal here that...
how concrete is it?
I mean, the W strings, we don't think of them as limits. We just define them a priori, okay? And then you can kind of argue, you can see structures. When you take the tensionless limit of a string, it is a Virasoro string for any epsilon, right? I mean, so where suddenly you have to integrate in high-spin gauge fields on the world sheet. How do you do that, right? I mean, they don't just come in a limit. You have to put them in, okay? So we prefer.
Yeah, but you see, if this were a world sheet description, these higher spin objects would just be obtained applying products of operators to the vacuum, like you do in ordinary string theory. The only difference is that you would not generate mass. So in some sense, it's a tensionless string, but it's a tensionless string of a finite type because it's
you have usually
space and
states or multi-particle states. They have mass. You have all the Regge trajectories. It's essentially the same type of formula that Matthias also described here. So you get multi-singleton states, okay? They have mass. So you get a huge string-like spectrum in this theory. We zoom in on the p equal to 1 sector.
Yeah, but if you want to connect to the Vasiliev system, you must remove the mass, right? Everything should be massless in that thing.
Yes, yes. So p equal means that you have a single copy of the symplectic manifold, and the operator algebra on that manifold becomes essentially p equal to 2, right? You have left and right action. So when you use Wigner-Will,
yeah, but then the world sheet description has to be constrained or something. It doesn't give you that because it will give you more, right?
No, the world sheet is a W. So we have these W algebra, we sum up the anomalies and we get critical dimensions. I mean, the fun thing here is that we can really argue. I mean, it's not a proof, of course, but we have a fun way of arguing for that you have to add this extra C's minus 2 system. This is our MAT2 that we used with Nicola and Ergin to build Frobenius-Simon theory. And on top of that, we need the Z variable. It comes naturally. And I can also tell, I mean, I didn't put it here, but in 5 dimensions, you get the Z space, which is still too complex holomorphic, okay? You don't, so in many of the models, the Y's and Z's are copies of each other. They literally sit in the same representation, but not in 5D. There, the matter and the anomalous sector, the Z's there sit in different dimensions. So that is, it looks funny first. It looks like it will break Lorentz invariance, but it doesn't actually. So we have a W string that we just define. I mean, it's like a constructive principle. I declare, you know, satisfy bling, 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 and then, you know, to solve for critical points. It's a bit similar to how you deal with Virasoro algebra. And then, of course, underlying, I mean, on top of it, maybe I should say, we have these background, we deform the background, we deform the Beer's operator, we write down these master equations, which are Vasiliev-like. I was flashing it there, of course, with multi-part on stage. You have to go into what the work of Misha of a couple of years ago, which is very nice, actually. So you can describe then, you know, include multi-singleton states. But it's really kind of man, this theory. That's the idea. And then string theory, you know, appears in limits rather of this, you see. That's how we think. You switch on, you break symmetries and go to some limits. It's a matter of, you know, which is the master theory here.
Okay, Misha, I see your raised hand. Please ask.
Thank you. I just wanted to interfere to the discussion and just with a little comment. I think what I'm glad that Per referred to that paper of 2 years old or 3 years. I just wanted to comment to the question of Augusto to some extent. I think that the story is a little bit more involved. I think that the true non-trivial tensionless string can be formulated in ADS or string-like model, let's say, string-like theory. And this is one of those higher-spin theories that were suggested recently. They contain huge tower of states and much more than usual higher-spin theories. So the point is that to go back to flat space, one should first break down higher-spin symmetries. And there is enough states to do that in those models. So there is not enough time of mind to do that, but there is enough space in terms of degrees of freedom in the theory to do that. And then if you do that, you will get something very much similar to the string theory. And what is really remarkable, and that's why I was kind of asking questions to Matthias, is that n-equal 4 super-Young-Mills somehow shows up in a very distinguished way in that construction from the perspective of ADS CFT. Just n-equal 4, no more and no less. So that is, I think, the scenario how the relation with string theory should appear. So you said that higher-spin theory is a limit of string theory. I believe that string theory is a limit of this extended higher-spin gauge theory. So this is my comment.
Yeah, I was referring to your theory with symmetric tensors. This is the.
Well, I could throw in there exactly if you redo the same computation with P or SU 22/n, you see immediately that n is 4.
I mean, see, it's very naive, but in string theory, if you just apply alpha minus 1, you get symmetric tensors, and that's called the Festerage trajectory. Now the question is how to get rid of the rest. And,
it's important here to think. Let's think, what does the string do in ADS? If you're in ADS 3, there's NS flux. The strings become large, like Gore-Maldacena strings, winding around infinity. You still have effectively Virasoro algebra acting as translation symmetries on that string. But if you're in ADS 5, strings do completely different things. They become very long and they have these cusps.
it's quite different, yes.
Like cusps, okay? And if you examine that, write down wave functionals, you rather get totally symmetric states. So the trajectory is craquelate, okay? The fundamental particle is no longer a cyclic string state, it's rather a totally symmetric string state. That's also what we think when we look at these W strings, that there is an operator algebra, there's a chiral ring that's totally symmetric. And that's also there in, you can see it in Misha's theory, there's like two branches of this equation. One that has like cyclic symmetry, and there's another branch, if I understood it correctly, which is more like total symmetry. So we find that that's very interesting. I mean, here one can see the spectrum on both sides. You can literally see the building blocks. We call them string partons there with Enquist many years ago. But these reincarnations of conformal particle field in different contexts. Okay, so that's formulate it together in the tensionless points, so to say, and then try to break the symmetries.
Okay, so it seems we exhausted all questions. So thank you very much for this evening session. Very interesting and very fruitful for me, at least.
Thank you.
So thank you very much, all speakers, and thank you very much all to everybody who came and was here. Okay. So we finish.
Bye.
Let's thank speakers.
Bye-bye.
Bye-bye, everybody.
Bye-bye.